To intro this, first of all, I'm not Joe Schneider. He was unable to attend. I'm Ryan Arnholtz at Dojo 5. And I will try to be as competent as Joe, at least in hosting, not necessarily in embedded development skills, but that's what Steve is here for. So I'll bring levity, and that's about it. So Dojo 5, we specialize in modern embedded developments. We have a services organization. We do a number of projects all over the country and all over the world with embedded developers in all pockets of the US and some global. We also have a product, EmbedOps, which is a CI for embedded orchestration platform. Steve is here today to talk about some top skills for modern embedded development. It's something that he's blogged about in the past and is personally passionate about. And so we'll have Steve take it from here.
All right, thank you, Ryan. So I'll just go ahead and get started here. So one of the things we have to remember is that we have people doing this type of work who are coming from a variety of backgrounds. So there's always this skills question. What skills do we need to do embedded systems development? And this is really a question from both an organizational and an individual career development perspective. So the organization needs to make sure it has the skills in-house to take on whatever projects they're responsible for. And then as an individual, you want to make sure that you're focusing on developing and maintaining the skills that will give you a long-lasting career. So we can update this question a little bit to say, what skills do we need to do modern embedded systems development? And I'll warn you that the 80s are over, so why do development that way? There are organizations that still do development, not much advanced from taking a floppy disk over to a flash programmer device, right, or an EEPROM programmer. We can do a lot better than that.
Really quick, what's changed since the 80s? Why can't we just do it the same way we do?
Yeah, so if we think about just what were we doing back 20 years ago? We were building locally on our workstations. We were making copies of files and putting them on disks or tapes or whatever sort of storage media we have, and stashing them in a file cabinet and maybe mailing ourselves second copies of it so we don't lose our source code. And we were doing manual testing, and so we run into all kinds of problems like builds that can't be repeated, lost source code, lost flash images, inability to program for different people. And so, and also one really big one was just inadequate testing, because most testing was just, someone sitting there manually doing some testing. And if today they forget to do a particular test that they usually do, well, it's just all kind of ad hoc and not very repeatable. So it's that repeatability and reliability of the process that is very important here. So let's look at some of the organizational skills risks. So, you might be using old development skills and practices that don't meet the needs of modern products. So those things that I went through. You might not have the skills in-house that are adequate to work with modern technologies. And your practices may actually impede progress. So you're slowing your work down trying to get it done. And further, your practices may create liability for you as a company. So, what if you lost the source code? You can't reproduce a build. What if you couldn't get a build done anytime soon? It's like, oh yeah, we'll be able to complete a build in a couple of weeks once we stabilize the branch and we've done a few other things. What if you didn't detect some critical failing in the product? Excuse me. One of the issues we have to deal with in embedded systems is that we build systems that can get people hurt, get people killed. And so we have a high level of responsibility for making sure that we thoroughly test things and detect critical problems that may arise in the field so that we can prevent them from getting out. And then what if you didn't have the skills to do a project? You've got a business you're trying to run and you can't do it because you don't have the people to do it. So what if you couldn't bring on additional team members effectively because your information and your practices are so archaic or poor that you're not able to bring people in? And then the opposite side of that, What if your employees got so fed up with this work environment that they left? So these are all skills risks that an organization faces from both a technical and a management standpoint. And then if we look at individual career skills risks, there are really three main things. First off, however many years of experience you have, what if your X years of experience are really just that same 1 year of experience repeated X times? So, you may think, hey, I have 10 years of experience, but, it's all just doing the same thing over and over again. The second risk is that you spend your whole career in one small corner of the industry. And this is actually a problem that I ran into myself. I spent most of my career for the first, 20 years of it in data communications. So, I know a lot about data communications, but I wasn't dealing with motors and sensors and things like that. So there's a whole broad spectrum of things in the embedded industry that I never dealt with. And so the final risk is, what if you just don't maintain versatility, right? You know one set of things, but that doesn't give you the ability to work on other things. And so what if your employees switched to a different technology that you didn't know? What if you were laid off or made redundant? You had to go find a new job. What if your employer went out of business? Again, you have to go find a new job. What if you want to work on something different? You're tired of this same old stuff. You want to do something different, or it's time to move onto another job. And what if all the technology has become obsolete? So all of your skills have basically aged out. And then as a result, what if you didn't have the skills to do a particular project? So are there any questions at this point?
There was only a question about the 80s, which I think you addressed.
Okay.
Anyone have any question about hair bands in the 80s or just embedded? All right, we'll move on.
Okay, so, what does it take to support modern embedded development? And, we have a photo there of a cross-section of a suspension bridge cable, and you can see skills are like a cable supporting this kind of bridge. It's multiple layered and intertwined. So this cable is a rope composed of bundles of strands made up of individual wires. There's no single thing that is enough all by itself. No single skill, no single part takes a whole load. They have to work together in support of each other. So taking that analogy, what are the major strands that support the skill set? So doing modern embedded development requires a mix of skills. Both the organization and individuals need to possess them. And one of the interesting things about embedded systems is these can be interdisciplinary skills and cross boundaries. And, if you look back on some of the projects you may have worked on or may have heard about, there are people who are doing software and mechanical engineering and medical devices and bioengineering and electrical engineering and, all of these different engineering functions, and they all mix together. So if we look at these major strands, then I like to think of them as the hardware skills, the software skills, the testing skills, the DevOps skills for embedded, and this is where we bring in what Ryan mentioned earlier, embed ops, the engineering mind skills, and then the soft skills. So one of the things that you'll often find in an organization is that you've got people with a very strong hardware background, electrical engineering, very strong software background, but they may not necessarily have the necessary skills in the cross-disciplinary functions. And so, your ideal mix of skills is a little bit of everything. And obviously, different people are going to have their specialties, but the more you can broaden that skill set and understand across disciplines, the more that you'll be able to work safely and work effectively with each other. So the detailed list of all these skills gets pretty big, right? I mean, we can make a gigantic wish list of, I wish I knew everything possible, but you don't need everything on every project. And you don't necessarily need to be an expert on everything. Obviously, you want to be an expert on a few things. That's the major strength that any individual brings to an organization. But in order to be able to function in those other areas, you don't necessarily have to be a complete expert in them. You rely on your team to bring that expertise together. But the interesting thing is that over the long course of an entire career, as you shift across projects and jobs, you may end up needing that large set of skills, that full set, and you may develop expertise on a number of different ones. So now let's take a look at the hardware skills. So, we can broadly break this up into an initial set of theory, practice, and techniques. And this is pretty much your basic electrical engineering type of thing. You've got your basic electrical theory, such as circuit theory and Ohm's law. You have the ability to read, understand, and interpret data sheets and schematics. So, we've all got our 1,000-page data sheets on some part and, our big pile of schematics with a bunch of squiggly lines. And so you got to be able to understand that no matter what your background is. Then we've got design skills. So we have the functional design, we have the layout, then we have various design rules and principles. For instance, are you doing a high frequency design, an RF design? Are you emitting RF? Are you receiving RF? Are you creating interference? Are you subject to interference? So those hardware design rules will help you deal with those issues. Then you want to have measurement and test abilities. So you got to know how to use a digital multimeter, an oscilloscope, a logic analyzer, because you're going to have to check things and take measurements and try and figure out why am I not getting information through this board. Then you want to have some basic assembly skills. So you want to be able to breadboard things because you need to throw together some sort of little prototype design or enhance it in an existing board. You want to be able to do some basic soldering and cabling management. This is definitely one of those areas for me as a software engineer where my skills are fairly low level. I'm not going to be doing any major board assembly, but I have the ability to do that when I need to. And then troubleshooting is just a huge hardware skill because, how many times have you gotten a board with no instructions about what to do with it? So you hook up a few things, you study the data sheets and the schematics, and you're not getting power, the board won't boot, it's crashing, you're not getting data in and out on your interfaces, or you're getting corrupted data. So you got to know strategies for troubleshooting that at the hardware level. And then if we look at the hardware elements that are involved, we start at kind of the higher level or the larger level at the scope of boards. So you've got dev kits and custom PCBs. You've got to be able to work with those, handle those, and then get down into chips, MCUs, CPUs, including their architecture, the various types of memory systems, and various types of interfaces between the chips. And so this is where you have to start understanding a lot of the internal details of the hardware. And then you get into all the various peripherals. So your GPIO, ADC, DACs, pulse width modulation, timers, various communications interfaces, and then data communications. So like I said, I had a strong background in data communication, so I was very familiar with Ethernet, but then getting into some of these other things, and everyone's using UARTs to connect their chips and talk to each other over simple interfaces. But now we've got Wi-Fi and BLE and cellular and just a huge grocery list of various communication technologies. So, the thing to do there is pick a set of those technologies that are relevant to whatever type of work you're doing and learn those in deep detail. And then you've got all the discrete components, right? When you look at a schematic, you see nice clear boxes that, oh, this is a microprocessor, this is a flash chip, this is, whatever. And then you have all those extra squiggly lines on the schematic, and you say, what are those things even doing? So your resistors, capacitors, inductors, understand the function they provide, why they appear on a design, why they are important. And then you have your various interconnect buses. So I2C, SPI, CAN bus, and then understanding all of the bus signaling protocols, down at the hardware level. So that when you put a logic analyzer on that, you can look at that that signal trace and say, okay, that looks right or that looks wrong. Then you have all your various sensors and other input devices. So keypads, buttons, things like that. And then your actuators and other output devices. And then another very big area is just power and signals in general. So what is your power supply? What is your regulation? How do you distribute the information? What is the capacity? What is the load? And very critically, what is the integrity of all of those? Because poor power integrity, poor signal integrity can just wreak havoc on a system. So you need to understand those concepts and how to chase them down. And so that's a quick list of hardware skills. Any questions at this point?
Unmuting. No immediate questions. I have a lot of questions, but you don't want to hear my questions. Where do I learn all this stuff, Steve?
Yeah, well, so that is part of the challenge. Now, a lot of this stuff, you may have, whether you went to an engineering school or a different college or don't have a college degree, you probably had some level of formal education that at least gave you an introduction to some of this, but you'll also need to be able to go dig this kind of information out on your own. And, once you get used to absorbing technical information, it's just a constant, continuous feed of that as we go on. And we'll actually talk a little bit more about that when we get to the soft skills. So now we'll go over to software. And here, once again, I've kind of split this into two sublists. So we have the general software skills. So, what are the languages that you write firmware in? C and C++, and now Rust is starting to come on scene. And then you're going to need to do some scripting and automation and tools. And so Python and Ruby and Bash and similar scripting languages are good for that. Now we have this corresponding, remember I said about reading data sheets and schematics, we have that same requirement for software. You have to read, understand, and interpret code. And sometimes it's a little bit of code, and sometimes it's hundreds of files, and you've got to understand how they all fit together. So developing the ability to sift through a code base and pull some ideas out of it is critically important. Because one of the things that we often find with embedded systems is that the documentation explaining what's going on is generally not very strong. So then we have general design issues, design skills. So you've got, first off, security. And I list that first because for a long time in this industry, we've kind of just ignored security. And so we've built ourselves a very vulnerable house of cards as a result. Now, security needs to be principle one in design. Everything else has to follow along. So from there, you have to deal with complexity and modularity, maintainability, testability, readability, all those abilities of the code and the code base, and then design principles, things like solid principles and object-oriented design and things like that. And then you want to have a good background in data structures and algorithms. And this is actually an area that doesn't tend to be emphasized for embedded development. But it's actually critically important because a poor algorithm can result in excessive resource utilization, poor performance, various other issues. So having a good background in the formal study of that is important. And that leads into complexity analysis for time and memory. So that's the big O notation, right? Is this constant order time? Is it linear? Is it quadratic? And so forth. And then we have memory management. So you have to understand your different memory areas, your static, heap, stack, and flash memory, how to make proper use of those in safe ways. And in fact, heap memory in some embedded systems is frowned upon or completely prohibited. And then you have to understand hardware control. So how do you do register access and device I/O? How do you do memory mapped register control? And then just as with hardware, we have a whole set of data communications software skills, except that now instead of understanding the hardware issues, Now you're dealing with the protocol stacks. So you might have the whole TCP/IP stack over Ethernet or over Wi-Fi, various BLE stacks, various radio stacks, and things like that. Then if we move over into the tools and techniques that are required for software, here we get into one of those modern practices, and that's source control, where Git is a very common tool. This is where we get away from, oh, look, I've made 5 copies of this floppy disk that I'm going to send out to the 4 winds so that I'm not going to lose my source code. Now, modern source control allows you to keep track of code and versioning and reproducibility. Then we have our various tool chains. So the cross compiler, linker, debugger, and flash programmer, sometimes these are all wrapped up into an IDE. Sometimes they're individual command line tools. And then testing. So I'll get into a little more about this, but test-driven development is a great way to do testing as well as actual software development. And that can kind of get off into a whole discussion itself. But test-driven development is really development driven by testing, right? Don't just think of it as testing. And then you have debugging. So you have to be able to know how to use various debuggers, GDB, OpenOCD for connecting to devices, and then all the various vendor pods and utilities for connecting to devices like J-Link and ST-Link and whatever other devices there are. Then you have to understand your runtime environment. And so we've got the bare metal versions of it and then the RTOS versions of it. And so this is where you're dealing with interrupts and concurrency, tasks or threads, drivers and kernels, board support packages, and HALs, hardware abstraction layers. So this is where you're getting into a lot of third-party code that you have to learn how to deal with and interact with and use properly. Then digital signal processing is a big functional area for embedded systems. So if you've got audio data or video data or some sort of other sampled data, you got to understand sampling and quantization, filtering, how to do various transforms on that data. Then we have control theory, which is where you're dealing with formal feedback loops, and we have various control regimes such as PID control and various other regimes. And so, understanding how to apply those and how to make them work. And then this last item on the list this is really new, very much something that was not part of the embedded world previously, and that is machine learning and computer vision. So this is a whole area of study all its own that requires a good background in inferential statistics. So, being able to apply those concepts now on a little tiny microcontroller is possible. We've got some amazing chips that are able to do object recognition, other types of pattern recognition with machine learning and embedded systems. And so there are just a million different possible applications of this. And so I'll pause here for any questions.
There was a question about hardware, and I don't think it was specific enough, but I think in general that there's interest in where do I find resources for these types of things. And so I'd mentioned a blog post at the end of yours, but in general, I think you wrote a great blog post on getting started with MCUs this summer. That's an example where we're not going to get into that depth of content in this webinar here, but the long form content around each of these topics is a great resource to not only get started but level it up a bit.
Yeah, and in general, I mean, the real secret to learning all of this stuff is to get yourself some hardware, some dev kits and the software that goes with it, the various packages that go with it, and even if it's just a real cheap little open source kind of thing, you can learn a tremendous amount just by connecting up a bunch of things on a breadboard and playing with it, right? And then you pull out your logic analyzer and you hook it up there. And now that logic analyzers used to be, big honking boxes that cost $100,000. Now you can buy one for a few $100s that fits in your pocket. So, get yourself a logic analyzer if you don't have one. Use it to probe a system, whether it's an Arduino or, an ST micro board or whatever. Get yourself some boards, play with them, go through some of the example code, and use your analyzer, maybe an oscilloscope, a DMM, just to play around and experiment with the system. And even sometimes when you feel like you're just doing random exploration, you're learning a tremendous amount. So it's that hands-on practice and trying stuff out and saying, okay, well, what if I change this line of code? What's that going to do to my analyzer trace? And tying all those things together is very educational. All right, so now for testing skills, as I mentioned, test-driven development is a great way of doing unit testing, but it's really a development methodology that results in having tests as well as developed code. You want to be able to do integration testing. And so if we look at unit testing as taking small isolated units of code that you can test off target, so you can test on your development host. Now integration testing is where we're starting to take those tested units, combine them together, and exercise them as a whole. And now you're starting to have to do on-target testing. And then hill testing is hardware in the loop. Now you're definitely doing some on-target testing against some external hardware devices. Regression testing is very important because sometimes it's very easy for problems that you ran into in the past to creep back into the code base for a variety of reasons. So you want to be able to confirm to yourself that once you've killed off a bug, it stays dead. So then we get into system testing, and there's a whole broad range of this. But once again, I put security at the very front of this list, because if your system isn't secure these days, you're just going to cause all kinds of problems. So security, penetration testing, testing your encryption, what data is being radiated out of your system inadvertently that you're leaking out to the world that someone might be able to abuse. Then we get into performance and load testing, resource utilization, and a critical thing for embedded systems is longevity, because there's a whole class of embedded systems that are remote sensing devices where someone builds this, they put a battery in it, and then they go bury it somewhere in the ground or in concrete or in a building or a roadway, and no one can ever touch it. So you want to make sure that that thing can run for whatever its intended service life is. Then you have various environmental testing, temperature, pressure, vibration, moisture, EMI. So one of the interesting things about embedded systems is, it's not a laptop sitting on your desk. This could be something built into an aircraft or a spacecraft. It's going up into the atmosphere, being accelerated at 10 Gs and exposed to, radiation. It may be something going undersea, exposed to moisture. So, you've got to be able to verify that you can deal with all of those things. Then you have various safety testing. And this gets off into a whole independent area as well, because safety testing is often something that if you don't really take a good focused approach to it, you may not really be adequately testing. And then finally, regulatory testing. So a lot of the devices that you may build, for instance, in the medical industry, the aviation industry, those are regulated industries. You have to be able to demonstrate that you've adequately met the regulatory requirements. Okay, so now embed ops skills. And here, you might ask, well, why do we need these things? And these really address the question of how long would it take you to get a release candidate out if we said, hey, do it now? Is it a week? Is it a month? Or is it an hour? And so the goal is, because we keep everything in a releasable state at all times, we have one ready to go that includes all the latest work. Or if we need to, we can make a change and have it ready as soon as the automated pipeline completes building and testing it, including exercising it in a hill test setup. So, that's the goal. That's the ideal. The skills you need to be able to do that, you need to know how to create and manage an automated CI/CD pipeline. You need to know how to do unit and hill testing. You have to be a master of the various build tools. And then you have to now, this is one of the other very modern additions, is manage and understand containerized environments. So Docker being a very common one. And then release management, versioning, archiving, distributing is a critically important skill, because this is where oftentimes a lot of confusion comes in and people have build problems because they're trying to pull in the wrong version of some library or some code. Then security scanning is also one of the modern requirements, because you basically have to assume at this point that anything that's connected to any sort of communications interface is going to be under constant attack. And then you have automation of your quality and performance metrics. So complexity, code coverage, boot time, what is your flash and RAM percentage used? And those are very important because that tells you how much headroom you have within your device to be able to add more things to it. And so if you want to see the Dojo 5 approach to this, I've got a link there to the modernembedded.com website. So any more questions at this point?
No questions. Keep on trucking.
Okay, now we get into a little bit more kind of voodoo engineering mind skills. So what do I mean by engineering mind? It means think like an engineer. These are the integrative and multidisciplinary skills that all come together. This is really the art of engineering. So for instance, in hardware, you want to know how to read a board and understand what's going on, plus the potential risks and issues that board may face. And so when I say read a board, that may be you pick up a board and you're looking at the devices that are on it, you're looking at the part IDs, you're looking at whatever information you can get by going through that hardware survey. And then you take the schematic and you're looking at it and comparing and figuring out how things are interconnected. And so the next hardware engineering mind skill is knowing what tools to apply. And tools here means, what are the things that go into doing this? So the processors, their architectures, the various devices, interconnects, techniques, and optimizations that you may apply. So this is integrating all of that knowledge from those earlier hardware skills into kind of a larger mind gelling. Now in software, we have very similar requirements, skills. So you want to be able to read a code base and understand what's going on, plus the potential risks and issues. So it's not merely, reading code, just finding what function you need to call, but saying, okay, what is this actually doing? How is it doing it? What are the, what does that imply? What's going to happen if I call this and if I make this change, and so forth. And so there's also knowing what tools to apply. So in software tools, the tools that go into building a system, we have algorithms and data structures, various design patterns, understanding concurrency mechanisms, and then, again, techniques and optimizations. Now, we can combine all of this into a combined hardware and software skill where we're able to map from the physical board to the schematics, to the data sheets, to the software code, and go back. And so you can say, okay, when I do this line of code, it's going to make that bit twiddle in this chip on this board. So being able to connect all of that stuff back and forth, not only is that important for just being able to make it work, but also being able to confirm in your mind that, okay, this is what I'm going to expect to happen when I do this in the code. So I can put a logic analyzer over here on the board and say, yeah, okay, that was what I expected. And then we have just this concept of basic engineering. And that's analyzing and understanding what you have in front of you, whether it's software or hardware. And instead of guessing or assuming, you understand it and then take it a step further to say, well, if I make this change, what are the implications? What should I expect? The software results, the hardware results, and be able to predict what can happen, then make the change and verify that it actually behaved the way you expected. And so this is really just an application of the scientific method, where you're observing, you're making a hypothesis, you perform an experiment, you analyze the results, and then you iterate on that as necessary to dial in on the solution. And sometimes we understand going in exactly what we need to do, but a lot of times we don't, especially if you're working with a third-party code base, someone else's board design. You're going to have to acquire all of that understanding, and that experimental method is really a great way to do that. And then there's the whole concept of problem bisection. This board is doing something wrong. Now you've got to isolate and work your way down the decision tree of potential causes of that and eliminate those until you get down to your root cause. So essentially a root cause analysis method.
Did want to pause for a question here. I think this timing is good and it wraps up a lot of the things you talked about so far. Alejandro had a question about if it's worth developing a sample project in which you can learn a lot of these skills. And so how do you, now that we've gone through all these things, how do you, and you'd mentioned, getting involved in the hardware, what sort of project might you come up with in order to practice these skills?
Yeah, so, one thing that I always recommend is get yourself a vendor dev kit, an ST micro board or something like that, or a Nordic board. Go through their SDK, their examples, and run that code. And, I know some people don't necessarily like vendor provided code because sometimes they feel that it doesn't really, it's all focused on just making the hardware act in the simplest possible manner without maybe applying enough software design principles. But it's a great learning opportunity because here's a direct example, and then you start playing with it. And maybe you don't like the design, so okay, then you do your own redesign of that function and make sure you can re-implement what they did. And then take some of those pieces and start combining them together. And so you may end up with some crazy monstrosity on a breadboard that has all kinds of blinking lights and switches and actuators and sensors that doesn't do anything functionally useful. But what it does is it forces you to learn how to make all of those things interact on one system, right? And then you might say, well, okay, let me do a bare metal version of this. Let me do a free RTOS version of it. Now let me switch to, some other RTOS, whether a commercial one or an open source one. And just, as you develop those individual skills, taking them the next step and changing something about it. So change one variable at a time. And as you master that, then you can go on to something else. And so by the time you're done, you may not end up with any useful item, but you've acquired a huge number of skills. And there will be many things that have gone wrong in that process. So you'll have acquired a number of troubleshooting and debugging skills along with the actual development skills. So, that's just starting from that simple hands-on and just, go crazy with it.
I've got another question or a clarification on hardware. And this it brings us back to the 80s. The question was, I'm in electrical engineering and I'm into hardware. How do I get more into firmware? How do these hardware skills and these firmware skills tie together? And I think, things have changed since the 80s, and that a lot of electrical engineering is now that piece is handled, but the firmware is becoming more complex. But how do you beef up those hardware skills? And that hardware skills slide that you had, is there an arc to it? Are there things that you learn early on, or is that, these are all the things you want to pick up over the next 20 years?
Yeah, and so that is actually a very important question. It's not like you're going to just acquire all of these skills at once, right? That's a lot of stuff to digest. And you can certainly get it fairly quickly at a very high level, but you want to get deep into it. And so the thing to do is to, again, I always fall back to the hands-on thing, because to me, that's really my favorite learning method. You know, I'll read books, I'll watch videos, I'll read blog posts, but until I actually get onto some hardware and twiddle some bits, you know, I don't feel like I really have the skill down. So for me, that's the final step where I'm integrating all that information and putting it into practice. And so that's useful for whichever set of skills you're trying to learn. You know, if you have an electrical background and you're trying to learn software skills, you're going to do that. If you have a software background and you're trying to learn electrical skills, you're going to do that, because it's this whole integrated skill set that you have to have an understanding of all sides of that. So to me, the key is to, you know, pick a few that seem to be for whatever your particular interests are, whether it's career interests or just kind of personal interests, you know, hobby interests, and say, you know, I want to go learn about that thing. So I'm going to get myself some hardware that does that thing. I'm going to find some example code to start with, and I'm going to play with that and then make it into something that's my own. And, you know, to me, like I said, that's my favorite process. But it's a very targeted thing where you have to pick something, and there's going to be a lot of stuff that you're just going to have to wave your hands at and say, oh, I'll deal with that later. But there's also going to be a lot of additional information that comes in that you didn't realize you're going to pick up. But because you're going through that whole experience, it all starts to sift in. And then as you repeat that on, you know, now that you've learned that thing, go learn this other thing, you start to integrate all that information together. And so, you know, the amount of time that it takes to do all this, you know, now we're talking about months and years. It's certainly not something you're going to do in a few days or a few weeks. So you just have to be reasonable, set reasonable expectations for yourself. You're not going to learn all of that stuff instantly. It's going to take time. And actually, that kind of leads into some of the soft skills. Any other questions at this point?
There was one more question. Are you familiar with leak code?
Yep.
Yeah, so I'm not sure if there's anything embedded on lead code, but you've mentioned so much hands-on, and lead code is almost deliberately hands-off. And so, you know, you could probably just approach your general philosophy to, you know, coding challenges and learning skills in a, you know, a virtual environment.
Yeah. Now, you know, one focus of leak code is data structures and algorithms. So if you're looking for a place to learn those, to exercise those skills, you know, that's definitely one use for it.
All right, let's hear about soft skills.
Okay, so
I have those.
soft skills. This is all the soft, squishy stuff that us engineers aren't supposed to care about or know about. You know, and we have a reputation as being kind of, you know, introverted, not very socially skilled, not very communicative. You know, those are stereotypes, but, you know, they certainly have some basis in reality. The real issue here is that all of this development is a team effort. And so you need to have interpersonal skills. You need to have empathy, compassion, humility, respect, and the ability to listen to other people. Because you're going to be in technical discussions where someone says, I think this is what's going wrong, and we've got, you know, you got to be able to listen to them. You may have your opinions, but, you know, be able to take in information from other people without biting their heads off, right? Empathy and compassion means you understand someone is having a problem with something, that you feel their pain. Compassion is driving you to help them out and deal with it. And humility is another, this kind of gets into another stereotype of the arrogant engineer, or, you know, arrogant manager who's saying, you will do it this way, and that's all you can do. And, you know, your code is terrible, my code is great. You need to have humility and accept, you know, what can go wrong, whether it's your code, accept that other people they're humans, they make mistakes, And so, be able to deal with people in a nice, respectful manner. And so then we get into communications, which is speaking, writing, and diagramming, because we need to convey information to each other. You need to help, you need to spread information to other people in your team, to your user base, to marketing, to everybody who's involved with a project or an end product. And, speaking is an interesting one to me, because I used to be just absolutely terrible at public speaking. If there were more than 3 people in front of me, I couldn't even get a word out. So for me, developing that skill was a difficult process. One thing that helped me with that was Toastmasters International, which has nothing to do with anything technical, but it's all about being able to get in front of people and talk, and talk about a subject that you understand. And then writing is important, because once you've written something down, that information is captured so that you can spread it around. It's, other people can read it, they can go back and reread it. And, a year from now or 2 years from now, you can go back and read what you wrote and say, oh, okay, now I remember. And then diagramming is just the visual version of that. We have various types of diagramming methodologies like UML and SysML, and then other less formal methods. But that's sort of the software version of what is a schematic for electrical engineering. Now, giving and receiving feedback that's definitely one of those interpersonal skills where it's easy for people to start bumping heads, because you're saying something bad about the code I wrote. That means you're disrespecting me. You have to be able to accept feedback. You have to be able to give feedback in a way that's not going to make someone defensive. And so being able to balance that, we come back to the empathy, compassion, humility, and respect. Time management is a critical skill, because all of this stuff can take a lot of time. We're trying to meet a schedule. We're trying to get a product out the door. We may have people waiting on it. If you're doing any kind of consumer products, there's a huge drive to hit certain ship dates so the products will be on the store shelves ready to sell. So time management, understanding how much time it's okay to invest in something versus how much time you have to say, you know what, I have to move on. And then deep focus is now taking beyond that time management and making that time that you use effective. So there are several people who have written some interesting books about it. Cal Newport is one where they're talking about, you're having to concentrate on something really complex here. You need to eliminate distractions. You need to be able to focus on that for, a good solid 2 hours or 4 hours or whatever it takes, and get the job done. And so this is actually an important thing, not only for the individual knowing how to manage their own time, but for everyone around them, including their management, saying, okay, we need to let that person do their stuff because they're deep into this. Right. And so you all know the concept of being in the zone. Getting knocked out of that zone is really a terrible waste of time, because now you've got to get back into it and focus back on what you were doing. Now we have asking for help. This is another problem that I've had in the past in my career. It's like, I'm going to fix this myself. I'm going to deal with this. But no, at some point you need to know when to back off and rely on your team and say, hey, you know what? I'm having a problem here. I need some help with this. And, this is something where it can be you have to kind of fight your ego there, because your ego is driving you to be independent and not ask for help. So you have to be able to do that when it's necessary. So that's a little bit back into time management, right? I invested whatever amount of time appropriate trying to figure it out myself. If that's not working, go ask for help. We have understanding with the customer, whatever that customer may be, what they want. and not just what they're asking for, because oftentimes they may not have sufficient technical knowledge to really even know how to form the questions, but you need to understand what they need and be able to convey that to them. So now we're back into listening to them, understanding what they need, and communicating back to them in information that they can understand and appreciate. Now we have the ability to learn new skills. And this is where we get back to that giant list of hardware and software and so forth skills, because it never ends. Technology marches on. Whatever you did in school, no matter how many degrees you completed, that was just the beginning. You know, whether you completed a master's degree 5 years or 10 years ago or last year, in 10 years' time, there's going to be all new stuff. So, you know, one example I always like to use is that, remember on the TV show Star Trek, and they had those communicators where they could talk to the Enterprise. Here you have a handheld communication device where you can speak to a spacecraft in orbit. Now we call them cell phones. So technology marches on and you have to keep up. So you have to have the ability to acquire new skills for the rest of your life. Which all of that rolls into the bottom line here. You need patience, persistence, perseverance, and a high tolerance for failure, because a lot of stuff will go wrong. And you can't let that get to you. You can't let it get in your way. You need to understand and learn how to manage those issues and move past them. So any questions here?
Yeah, we have a couple questions. Also, I want to make a comment. You'd mentioned communications. This kind of leads into one of the questions around documentation, but you had a quote in one of your blog posts about treating documentation or your engineering notebook as a guide for your future self. And I think across our team, I've noticed that anytime somebody talks about documentation and engineering notebooks, there's a 100-message Slack thread on best practices. Like, engineers geek out about like how they want to make sure that they're not only educating their future self, but also we work on a number of client projects where we might work on it for 3 to 4 months, and then the next 5 years, people might be reading the documentation. So there was a question around specific skills required for documentation, and if there's any tool or software recommendations for that.
Yeah, so actually there's, just recently, one of my colleagues showed me a very interesting documentation model. I'll have to provide the link separately, but the idea was that you've got 4 types of documentation. You got tutorials for the beginner where you're leading them by the hand and assume nothing. You have how-to guides where you're saying, okay, you want to do this specific thing, you know a little bit about what you're doing, here's how to do it. And then you got references, which are, this is not focused on any particular task at hand. This is just the reference for, here's all the parameters to this function and what they mean, so forth. And then you've got explanations. So the explanations are kind of the place where you can step back and say, okay, well, we've got all this other information. Let's talk about it. What does it imply? What are some options and alternatives? And so those 4 types of documentation, I thought made a really good model, because in any given project, you're going to have different needs for different levels of that at different points. And so I will provide that information as a link to distribute.
Since we just have a few minutes left, I wanted to make sure you get to your wrap up here. But one of the themes here is, how do I move from, I have skills in this area. How do I move from a hardware person to working on FPGAs? How do I move from a mobile app web developer into an embedded developer? So if you can kind of wrap that up in your summary, that'd be good.
Yeah, so just quickly in the summary, there are a lot of skills that you might need to get a project done, but not every project is going to need all of them. So, don't look at that whole list and say, oh, I can never do all that. Don't get intimidated by it. Pick things out of it. So it's a varied mix that will change over time and across projects. And the broader your range is, the more capability you have, both as an organization and as an individual. Skill gaps are major risks to you as an organization or as an individual, because those are potential problems that can get you into serious trouble. So you want to take action to fill them. And so the actions that you should take are, you want to seek out whatever sort of introductory material there is just to help you get oriented into the thing. And sometimes it's just a matter of, go look it up in Wikipedia, read that page, start going through the bibliography of that page. And for me, bibliography chaining is a great way of getting more information, because it's always interesting to see, okay, this author said this one sentence or one paragraph about this topic, but what did they use as a reference? So let me go look at that. And you start spreading out your information. And so that's how you acquire the initial set of information. And then, again, get yourself some hardware and start playing with it. And one of the great things about hardware these days is that you can buy all kinds of development kits with every kind of technology possible for, $10, $20, $100. It used to cost tens of thousands, hundreds of thousands of dollars to get development hardware and tools. Now, for a total investment of maybe $1,000, I mean, you can get yourself an FPGA development board and the software to practice with it. You can get yourself an online course that takes you through some examples. And so, whether it's FPGA development or, going from a JavaScript developer into, a C embedded developer, all of that stuff is now accessible. The key is back to that learning skill. You have to be able to take that information and apply it directly yourself, right? So you have to be self-motivated, self-driven, know how to go find information and, extract what you need from it and apply it. And really, I mean, that just generally applies everywhere. So just whatever topic it is you want, just go look for some of that initial information. And that starts the branching tree of knowledge that will take you through all of it.
All right, we don't have any other questions. Do you want to go to the last slide here? We can wrap up. So thank you, Steve. Very informative. I'm still a long ways from being an embedded developer, but someday.
Get yourself some boards.
I've got this. It's been sitting on my desk for 2 months. How do you start with a Jetson Nano? That's my question. It might be a little too beefy for me. So we have an upcoming webinar. The time is to be determined, but we're going to be putting together a webinar with iSystem on intentionally building quality into your organization with CI. And then all of Dojo 5 will be in Nashville next week. And so we're getting together with Matthew Eshelman. He put together a fantastic blog post in 2020 that kind of maps, in the same way that the Joel test 20 years ago had changed a lot of development and some philosophies around it. Matthew put together some really good thoughts in a blog post. So check that out on the Matthew test. And so we'll be having a conversation with him in Nashville. If you happen to be in Nashville, you can stop in. You can register on our site at dojo5.com/events. This webinar was inspired by a blog post that Steve had written this summer. You can check that out. It's on embeddedrelated.com. A fantastic resource for a lot of the things that Steve talked about, not just his own blog post, but some great writers on there, some good information resources. If you want to dig in a bit deeper on some of the content in his webinar today, you can find that in his blog post there at the tiny URL. So if there's any more questions, I don't see any. I think we're good to go. So thank you very much for attending. Thank you for your questions. And we look forward to seeing you soon.
All right. Thank you, Ryan.